dear student friends, morning all of you. I welcome all you people in this wonderful online Google Classroom. As we have discussed in the last class, the topic what we are continuing this class also is nothing but your morphine and opium alkaloid. As I told you in the previous class, that morphine, the chief source of morphine is a plant. Its name is papaver somniferum. Papaver and somniferum is the name of botanical name of that particular plant from which we extract this morphine opium alkaloid. While extracting, there are three different opium alkaloids are there in this particular plant. One is morphine, another one is codeine, and the third one is thebaine. Morphine, codeine, and thebaine. Anyway, our discussion is purely morphine because morphine is the chief opium alkaloid. What we get from this particular plant by the extraction when we carry out. There are three different structures drawn on the board just to recollect your memory, recall your memory. One is, the topic is morphine, its molecular formula is C17H19NO3. This is the structure of your morphine. In all the three opium alkaloid, the basic nucleus present in all the three opium alkaloid is your phenanthrene nucleus. Three-membered aromatic ring is the basic nucleus that is present in all the three alkaloids. 1, 2, and 3. This nucleus, as I told you in the last class, is your phenanthrene nucleus based on which all the three alkaloids are constructed by nature. Now come here. This is the structure of morphine. We have two hydroxyl group in morphine, one oxygen in the ether linkage position, one nitrogen in the tertiary position, to which there is a methyl group. This is the basic structure of your morphine. Morphine consists of one primary alcohol and one secondary alcohol. How we have arrived at this conclusion, that we will discuss later. Anyway, time being, keep this in your memory that morphine consists of one primary out of the two OH, out of the two hydroxyl group. One is primary alcoholic, another one is secondary alcoholic, and the nitrogen in the tertiary position. Remember this. Okay. Now come to the next structure. Your codeine, second opium alkaloid, codeine. Codeine also remains same, similar to your morphine. The only difference here is one OH, one hydroxyl group is replaced by your one methoxy group. OCH3 is there instead of OH. What we have in morphine is OH, and in codeine, one OH is replaced by your one methoxy, that is OMe. The rest remains same. This is your codeine. Now come to the third one, that is thebaine. In thebaine, compared to your codeine, the structure remains same, basic nucleus remains same, tertiary nitrogen, one methyl, one epoxy oxygen, everything remains same. But the two OH what we have in morphine is replaced by two OH, two methoxy. In codeine, just one methoxy and one OH. And in the last one, that is thebaine, no OH, both the OH are replaced by your methoxy. These are the few things that I want to recollect before we discuss the structural elucidation of morphine that we will discuss now. I told you that in morphine there are two hydroxyl group, one nitrogen in tertiary position, one methyl is connected to tertiary nitrogen, one oxygen in ether link, that is in epoxy position. Right. The entire thing we will discuss. There is one phenol 3 nucleus is there that we will discuss now. Yes. Structural elucidation of morphine. Structural elucidation of morphine. This is the one we are going to discuss now. To discuss this, we need to proceed slowly. What are the different reactions, important reactions based on which we are going to conclude the presence of hydroxyl, the presence of ether link, and the presence of tertiary nitrogen, and the presence of primary alcoholic, and the presence of secondary alcoholic, etc. etc. We know that nitrogen is in the tertiary state as far as the structure of morphine, structure of codeine, and structure of thebaine is concerned. The first reaction, what we are discussing now is morphine when treated with acetyl chloride gives, keenly observe, morphine when treated with acetyl chloride gives diacetate, nothing but acetate substituted morphine is the product what we get now after acetylation is over is called heroin. Morphine gives heroin. Using acetyl chloride, morphine gives heroin, a byproduct. Very, very dangerous. The heroin name itself is a very bad one. It again as ENS depressant. Most of the people are consuming this heroin not for your medicinal purpose, simply for entertainment purpose, for enjoying purpose, because it stimulates your, after depressing the CNS, one goes easily to the excited state. There he can enjoy just for a few hours. After that he will come down. And once a man is addicted with this heroin, opium alkaloid, it's very difficult for him to come out of this addiction. And for this reason, we used to say that this is a highly dangerous one because it is depressing your central nervous system. Always, once if you are addicted with this heroin, whatever we give to that concerned, that person, he will never accept the rest of the things. He will only, always, he will in search of that particular heroin because of that particular addiction. Like once the alcoholic addiction is there in a person, he will never come out. Slowly, it's very difficult for him to come out of that particular addiction. Therefore, it's highly dangerous. The first reaction is morphine gives diacetate derivative, that is nothing but heroin, and also gives dibenzoate. When treated with benzoyl chloride, you will get dibenzoate. Heroin is a diacetyl derivative of diacetate of your morphine is a heroin. Dibenzoate of morphine you get when treated with benzoyl chloride. Both these confirms the presence of two OH groups in your morphine. Both these reactions confirms the presence of two OH groups. only when there is a hydroxyl group. The added acetyl chloride or added acid benzoyl chloride for benzylation and for your acetylation, acylation. This particular conversion is possible. Heroin is possible by replacing this hydrogen by your CH3CO on treatment with your acetyl chloride. The product is acetate, diacetate. Similarly, another OH is getting substituted, that is replaced by the replacement of hydrogen by CHCO, CH3 is taking place. The product then is your CO, CCH3, CH3COO. Acetate. Again there is one acetate, CH3. Two acetate group gets replaced by your the proton of 2-hydroxyl group. When there is only 2-hydroxyl group, the reaction called acetylation is possible. The formation of diacetate derivative as well as the formation of dibenzoate derivative is possible only when there is a 2-hydroxyl group. It is not giving the picture on what nature of the hydroxyl group is, whether the hydroxyl group is either primary alcoholic or secondary alcoholic. It gives, this particular reaction gives a clue on the presence of 2-hydroxyl group. Anyway, we know very well that there are 2 hydroxyl groups are there in morphine. So the reaction explains clearly that the 2 hydroxyl groups are there in your morphine. Are you clear, friends? See the reaction. Morphine gives diacetate derivative, that is heroin. Morphine also gives a dibenzoate derivative. Both these confirms the presence of 2-hydroxyl group in your morphine. Now come to the next one. The next reaction explains the nature of hydroxyl group. That is, when you treat morphine with ferric chloride, similar to when you are treating phenol, say for example, you go to phenolic chapter, a specific reaction that confirms the presence of phenol is ferric chloride test. What we do in ferric chloride test confirmation? We treat the phenol with ferric chloride. We heat the phenol with a little of ferric chloride solution. And after heating, when there is phenolic OH group is there in the phenol, that is in the suspected given organic compound, it will give you either green color or purple color. Green color or purple color. A specific reaction that confirms the presence of phenol. Green, blue, red or purple. Either color, either of these 4 colors you will get when there is a phenolic OH. This is the particular test that we use to confirm the presence of phenol. Now you apply the same test in confirming whether we have a phenolic hydroxyl group, that is primary alcoholic group, in morphine or not. We can use this particular test. What we do? Use the same thing. Morphine. You allow the morphine to undergo reaction with your ferric chloride similar to your phenol. In the place of phenol, you are taking now, in this case, the morphine. Morphine on treatment with ferric chloride gives the same coloration what we get in the case of your phenol. What it shows? It implies simply the presence of phenolic hydroxyl group. In the phenol, the hydroxyl group, there is only one hydroxyl group is there. That hydroxyl is in the primary alcoholic nature. So this particular reaction confirms the presence of primary alcoholic in your morphine. So out of the 2 OH, you know very well, you recollect in memory the structure of morphine. In the morphine, there is 2 OH group. In between, there is O link group. That is, an ether link is there in between. 2 OH groups are there. Out of the 2 OH group, out of the 2 hydroxyl group, one is primary alcohol. That is confirmed just now with the help of this ferric chloride test. Okay? Are you clear now? So one hydroxyl group is in primary alcoholic, nothing but primary alcoholic group. OH is primary alcoholic. Now we are moving little bit. The next reaction, not only this particular thing we are confirming the presence of primary alcoholic, also the morphine gives, when you allow the morphine to react with your sodium hydroxide solution, it dissolves in sodium hydroxide to form monosodium derivative of morphine. Monosodium derivative of morphine. In the case of phenol, when you dissolve the phenol in sodium hydroxide, very much soluble in sodium hydroxide, immediately phenol will be converted into sodium phenoxide. Sodium phenoxide, like this. O minus Na plus. This is your sodium phenoxide. Yes, same product you get in the case of morphine also. When you treat morphine with sodium hydroxide, you will get monosodium substituted morphine. This is phenol. Let us assume this is your morphine residue. So we get monosubstituted morphine when you allow the morphine to react with sodium hydroxide. This confirms very easily the presence of your phenolic hydroxy, phenolic OH group. There are 2 OH we know. Out of the 2 OH, there are 2 tests we have discussed now. One is ferric chloride test. Ferric chloride is a unique test that we normally use in the laboratory to confirm the presence of phenol. Phenol, when treated with your ferric chloride, gives 4 different colors, either blue, red, purple or green color, that confirms ultimately the presence of phenol. Similar test we apply in the case of morphine also. Morphine, if the OH group present in the morphine is exactly like your phenolic hydroxide, then ultimately it has to give. And the same thing we get when the reaction is carried out with the help of your morphine. Morphine treated with ferric chloride gives the same result as we get in the case of your phenol. So one hydroxyl, the ferric chloride test confirms the presence of phenolic hydroxyl group. That is, one is in the primary alcoholic nature. To confirm that one, we are proceeding to the next reaction. The next reaction is allowing the morphine to react with your sodium hydroxide. It will dissolve immediately into sodium hydroxide like your phenol. Ultimately, the product is monosodium substitute, that monosodium derivative of your morphine. Again, this confirms the presence of the same phenolic hydroxide. So there are 2 tests we have discussed now. One is ferric chloride to confirm the presence of phenolic hydroxide. Another one is dissolving the morphine in sodium hydroxide so that we get monosodium derivative of your morphine. This is another test, that is one more evidence to confirm the presence of your phenolic hydroxide, that is primary natured hydroxyl group. The second OH, if the 2 OH groups are secondary, then we can't expect, we never get the above reactions. Above reactions not at all possible with the secondary alcoholic. Because we have a morphine, because we have a primary alcoholic in morphine, the morphine gives ferric chloride, morphine gives the sodium hydroxide test. Now the second hydroxide is naturally the secondary alcoholic. For this we have number of proofs. One by one we will try to see now. So far we have discussed many things. To try to recollect all those things in your memory. Now what to do to confirm the secondary hydroxyl? We are proceeding further in the structural elucidation. Now you allow the morphine to react with halogen acids. Morphine immediately gives monohalogenoid derivative. Monohalogenoid derivative. Monohalogenoid derivative. Morphine, when treated with halogen acids, gives MX. Monohalogenoid derivative. This again confirms the presence of 1 hydroxyl. Again confirms the presence of OH group. It is not confirming just 1 OH or 2 OH. It is confirming again one more proof to confirm we have a hydroxyl group. We have hydroxyl group, and that too just only one. Remember, only one hydroxyl. We have two. That is a different thing. Listen all my discussions. Then we will come to know very clearly why I am insisting that particular point. Now, morphine when heated with methyl iodide further in presence of aqueous sodium hydroxide, morphine is methylated to give codeine. Morphine treated with methyl iodide in presence of aqueous potassium hydroxide, methylated morphine we get. Methyl group is introduced into morphine. You are treating morphine with methyl iodide in presence of aqueous sodium hydroxide. This ultimately gives morphine methyl, that is morphine is methylated to give codeine. Morphine is methylated to give codeine. One methyl is introduced into morphine. You just recollect in your memory the structure of codeine. In the codeine, what we have seen is this. This is OH and this is OCH3. This is codeine. Methyl is introduced. Methyl is introduced. That is called methylation is possible in just one hydroxyl group. This again confirms the presence of only one OH group, presence of only one primary hydroxyl group. Primary hydroxyl group. This introduction of methyl is not possible in secondary hydroxyl. We have some other proof to confirm the presence of the secondary alcoholic. So this particular product is your codeine. So on methylation, morphine gives your codeine. Morphine when treated with methyl iodide in presence of aqueous potassium hydroxide gives codeine. Its molecular formula we know that C18H21NO3, 1 carbon higher, 3 hydrogen higher when compared to your just morphine. So 2 hydrogen higher compared to your morphine. CH3 you are introducing into your morphine so that the final product is your codeine. This confirms the presence of again one phenolic hydroxyl group. And the next reaction what we are going to discuss is morphine on oxidation gives a ketone. Codeine, codeine on oxidation gives codeine, a ketone. Remember, now we are discussing that particular important point. When there is a secondary alcoholic, CHOH, secondary alcohol on oxidation gives only ketone. So similarly, codeine, since the codeine consists of your secondary hydroxyl group, both morphine and codeine consist of the secondary alcoholic. This is the reason why the codeine on oxidation gives your codeine. So naturally, this particular reaction confirms the presence of your secondary hydroxyl, secondary alcoholic. Secondary alcoholic is also there. This is confirmed by the oxidation of codeine into codeine. So this is your proof to confirm the presence of secondary hydroxyl group, secondary alcoholic group. To confirm the primary alcoholic group, we have number of reactions that we have discussed already. To confirm the presence of secondary alcoholic group, we have this particular reaction. Codeine on oxidation gives codeine, a ketone. This is the ketone formation from alcohol is possible only when the alcoholic is secondary. Only when the alcoholic is secondary. Otherwise, the primary alcohol will not undergo oxidation. It will not give you the ketone directly. So secondary alcohol is now converted easily into ketone on its oxidation. This confirms the presence of secondary hydroxyl. Secondary hydroxyl. Based on the above thing, we are now arriving the clue on the structure of the codeine. Codeine, based on the above discussion, it is therefore confirmed that this is nothing but monomethyl ether of morphine. Monomethyl ether of morphine. Monomethyl ether of morphine, that is C6. OCH3 is there, and the second one is CHOH. Yes, this is for codeine. Monomethyl ether, OCH3, methoxy. We have only one methyl, therefore this is monomethyl ether of morphine. The morphine structure, the basic structure of morphine remain in the case of codeine also. The only difference is in morphine, here there is just one OH and the second is CHOH. One is primary hydroxyl, second is secondary hydroxyl. One is primary alcoholic, second is secondary alcoholic. In the case of codeine, the structure, slight difference in the structure is one primary alcoholic is converted into, that is in the place of primary alcoholic, what we have in the morphine is simply replaced by OCH3. In that case, the structure is different. The structure is the compound now is changed into codeine simply by replacing one primary alcoholic into OCH3. The product what we get is codeine. Also, one more clue, similar in connection with this, codeine absorbs just one molecule of hydrogen on catalytic reduction. Confirms this particular codeine also, because the codeine and morphine almost same. The only difference between the two is in morphine just one primary alcohol, whereas in codeine there is no primary alcohol, one OCH3 in the place of primary alcohol. So both codeine and morphine consist of just one ethylenic double bond. Ethylenic double bond is there, just one. Because of this, it absorbs just one molecule of hydrogen on its catalytic reduction. Using proper catalyst, when we go for reduction, both morphine and codeine absorb just one hydrogen molecule. This confirms the presence of one ethylenic double bond. Just one double bond is there in both codeine and morphine. These are the few clues that we reached so far after the discussion of plenty of points, or that is after the discussion of all these points. Have a look. The codeine is this, morphine is simply OH. You can't see this OCH3 in morphine. OH is there in morphine, whereas in codeine OCH3. In thebine, no secondary alcoholic, both OCH3. So morphine, one primary alcoholics, one secondary alcoholic, one O in epoxy position, one nitrogen in tertiary position, and to which there is one methyl. Codeine, one CH3, one secondary alcohol, one nitrogen as usual tertiary. Thebine, one nitrogen as usual in tertiary position. both OH is replaced, both OH of your morphine is replaced by 2OCH3 is the value. That's all I want to discuss in this particular class, because the restricted time is almost over. We will try to discuss the continuation of this in the next class. Till then, take care, stay home and stay safe. Thank you.